Good morning, guys. Today we'll talk about zeros of polynomial functions, and let's start with this example. So it says show that x plus 2 is a factor of that polynomial and find the remaining factors. Use the factors to determine the zeros of the polynomial. So I hope you remember from the previous lesson, we found that if a polynomial is divided by a factor of the polynomial, if a polynomial f of x is divided by, let me use black. If a polynomial f of x is divided by a divisor, say x minus k, and this divisor is a factor of this polynomial, then the remainder will be 0. The remainder will be 0. This is kind of what the remainder theorem is, and that says that if the function f of x can be expressed as the divisor x minus k times the quotient, which is usually also a function of x, plus the remainder. Sometimes the remainder is a function of x, sometimes it's not, but this is the general remainder theorem, that any function f of x can be written as quotient, divisor times quotient plus the remainder. Now if this divisor is a factor, then this remainder is going to be 0. If x minus k, which is the divisor, is a factor, forgive my handwriting, then the remainder is going to be 0. This is what we talked about in the last lesson, last week on Friday. So this basically means that if you substitute x is equal to k in this expression, in this function f of x, if I substitute x equals k, then f of k is going to be 0 because k is a 0. So trying to show you a simple example of that is, imagine you have f of x equals x squared plus 3x plus 2. Now I know, because I'm the one who has made this question, that this one, the zeros are x is -1 and x is -2. Since those are the zeros, I know this ahead of time, but since these are the zeros, it means that if I substitute f of -1, my function will give me 0. And you can see that that's true, because if I put -1 here, that's now -1 squared, which is 1. -1 times 3 is -3 plus 2, that gives me 0. If I do the same thing for -2, I expect it to be 0 because I'm substituting for a 0 of that polynomial. And yeah, so if you substitute that, you will get 0, because this is 4 plus 6. 4 minus 6 plus 2 is 0. And what that also means, that since my x is equal to -1 is a 0, that implies that x plus 1 is a factor. I'm getting this x plus 1 from setting this equals 0. And getting this x plus 1 from taking the -1 on this side. And then that will be x plus 1 is equal to 0. That means x plus 1 is a factor. And that also means that since x is equal to -2 is a 0, x plus 2 is a factor. Let's just recap of the previous lesson. How can we use this knowledge to find the other zeros or to determine the other factors? So in this example, since if I had been told, without knowing, if I had been told that x plus 1 is a factor, I could have used long division or synthetic division to find the other factor, which is x plus 2. So that's kind of what we're doing in this example. Sorry, this is a long review, but yeah, this is what we're doing in this example. They've told us that x plus 2, no, they want us to show, that x plus 2 is a factor. If x plus 2 is a factor, then when I divide this expression by x plus 2, I expect to get a remainder of 0. So let's see, I'm going to use synthetic division. The coefficients are 1, -6, -1, and 30. And when I'm using synthetic division, I compare this to x minus k. When I compare that to x minus k, I hope you can see that -k is equal to +2, so k is equal to -2. First step is I drop the 1, then I do 1 times 2 times -2 is -2, -6 plus -2 is negative 8. Negative 8 times negative 2 is positive 16. Negative 1 plus 16 is 15. 15 times negative 2 is negative 30. And 30 plus negative 30 is 0. So since I have got a remainder of 0, my remainder is equal to 0. This proves that x plus 2 is a factor. Therefore, x plus 2 is a factor. Now, my quotient that I get from dividing this quotient can, because remember, since this power is x power 3, then the power of this should be x power 2, x power 1, and x power 0. So my polynomial, my whole f of x, can be written as x squared minus 8x plus 15 times the divisor, which is x plus 2, plus the remainder, which is 0. So basically my expression is x squared minus 8x plus 15, this is 15, times x plus 2. I have used one factor to find another factor, technically a quotient, but this other factor is still in terms of a quadratic equation which can be factorized. I hope you remember your UFOs. The factors of x are x and x, or you remember your factorization. The factors of 15 that I can use are 5 and 3. I need to manipulate these factors such that their sum is negative 8 and their product is 15. In order for that to happen, they both have to be negative. Then I do this. Here I am simply factorizing a quadratic equation, which you can do according to any method that you know. So my factors there are x minus 5 and x minus 5 and x minus 3, and remember a factor which was already there was x plus 2. So my polynomial f of x, which was all of this, has been simplified to x minus 5, x minus 3, and x plus 2. So those are the factors, minus 3, minus 5, minus 3, and plus 2. Since I know that x is equal to negative 2 is a 0, because if x plus 2 is a factor, that means x is negative 2 is a 0. How do I get that? Set it equal to 0. Set the factors equal to 0. So to get the zeros, I'm going to set each of the factors equal to 0. So I can start with positive 2 equals 0. This was a factor. The 2 goes over to that side. So I know a 0 is x equals negative 2. And I can write that as a coordinate, negative 2, 0. The other one is x minus 5 was a factor. I set it equal to 0. Then I'll get x is equal to 5, which I can write as a coordinate, 5, 0. And the last one, x minus 3 equals 0 is a factor. Then that implies that x equals 3 is a 0 as a coordinate, 3, 0. So my zeros, if you want to write them aesthetically, are negative 2, 0, 5, 0, and 3, 0. I have used my knowledge of synthetic division and the remainder theorem to find the zeros and the factors of this expression. So that's what has happened. Right, the factor theorem, kind of what I touched on in the previous screen, is that if k is a 0 of f of x, k is a 0 of f of x if and only if x minus k is a factor. And it works backwards. If x minus k is a factor, then k is a 0. How do you get k? Set x minus k equal to 0 and then solve for x, which is x equals k. So if x minus k is a factor, k is a 0. Or if k is a 0, then x minus k is a factor of fx. K can be a real or complex 0 because equations can have imaginary numbers in their solutions. Alright, so let's try this example. We're trying to construct a quadratic equation whose zeros are these ones given. Now remember from the previous screen that if k is a 0, then x minus k is a factor. So they've given us two zeros. They've given us x equals 2/5 and x equals 3/4. So if these are basically k values, they've given us k values. So if these k values are zeros, then that means that x minus k are factors. Since these are zeros, then that means x minus 2/5 is a factor and x minus 3/4 is a factor. So I can simplify this because remember the factors are equated to 0 to get the k values. So if I simplify this, it will be 5x minus 2 equals 0. If that's confusing, you can take it slow. LCM is 1. 5x minus 2 divided by 5. If you cross multiply, the 5 cancels out. If I simplify this as well, it's 4x minus 3 over 4 equals 0, but the 4 cross multiplies and cancels out. So I have two factors, therefore my f of x could be 5x minus 2 times 4x minus 3. When I expand that, 5x times 4x is 20x squared. 5x times negative 3x is negative 15x. Negative 2 times 4 is negative 8x. Negative 2 times negative 3 is positive 6. Collect like terms. 20x squared minus 15 minus 8 is 23x plus 6. And something interesting about these two values, the first value and the last value, the leading term and the last term of this polynomial. Let me show you here in the next video, in the next screen, sorry. So what happened is x was equal to negative 2 or x is equal to negative 3 over 4. I made those into factors by equating them to 0. From my quadratic equation, this is what was on the previous screen. But what I want to call your attention to is these values. 5 times 4 is 20 because 20 comes from 5 times 4. And interestingly, 2 and 3 product gives you 6. And I hope you can see that 2 and 3 were the numerators of the k values, or of the zeros. And 5 and 4, which give me the leading term, were the denominators of the k values. 2 and 3 were the numerators, they give me the last term. So this tells me something. This brings me to an interesting mathematics conclusion, which is called the rational zero theorem. And it states that if a polynomial has so many terms but has a first term and a last term, and it has integer coefficients, right? If it has integer coefficients, meaning that these values, the first term and last term, are integers, then every rational zero, you can think of it as a fraction zero, or basically every zero of f of x has the form p out of q, right? P out of q, where p is a factor of the constant term. P is going to be a factor of this last term, and q is a factor of the leading coefficient. Q is going to be a factor of this first coefficient. As you saw in this previous example, this p, what was it? So basically p over q, p was a factor of the last term. This 2 is a factor of the last term, which is 6, as you can see here. 2 times 3 is 6. And this p also of another 0 is also a factor of the last term. And q, the denominator, is a factor of the first term. 5 is a factor of 20, and any other rational 0 in that polynomial will also be a factor of that leading coefficient. Let's see how this works. So if I want to use the rational zero theorem to list all the possible real zeros, I know that if a polynomial has rational zeros p out of q, then p is going to be a factor of the constant term, or the last term, right? This constant term is going to be a factor of this term, and q is going to be a factor of the leading coefficient. Let me just call it first coefficient. You have to make sure that it's arranged in order for this pattern to work. So what I'll do is list all the factors of negative 4, and then list all the factors of positive 2. The factors of positive 2 could be 1 or 2, or negative 1 or 2, or negative 2, sorry. So the factors of positive 2 could be plus or minus 1, or plus or minus 2. The factors of negative 4 will be plus or minus 1, plus or minus 2, and plus or minus 4. Why am I using plus or minus? Negative 1 times negative 4 could give you, negative 1 times positive 4 can give you negative 4, or positive 1 times negative 4 could give you negative 4, so I also need to include the negatives. I'm going to use this combination of P out of Q to determine to list all the possible real zeros of f of x. So I'll start with, remember P is the factors of the last term, so these ones have to be on top. So for each of these factors, for each of these p values, it could have a denominator of either of these. So my real zero could be plus or minus 1 over, so this one, the first one, I'll start with the first one, plus or minus 1 over plus or minus 1, plus or minus 1, or it could be this same one divided by plus or minus 2. So plus or minus 1 divided by plus or minus 2. That's one possibility. Another possibility is, now I move to the second one, plus or minus 2 over plus or minus 1, or it could be plus or minus 2 over plus or minus 2 over plus or minus 2. The third one, the third and last possibility could be, this is on top, remember p is the factor of the last term, so plus or minus 4 out of plus or minus 1, or plus or minus 4 out of plus or minus 2. Let me see what each of these comes to. Plus or minus 1 divided by plus or minus 1 is the same thing as plus or minus 1. Plus or minus 1 over plus or minus 2 is the same thing as plus or minus 1/2. Moving on, plus or minus 2 out of plus or minus 1 is the same thing as plus or minus 2. Plus or minus 2 divided by plus or minus 2 is the same thing as plus or minus 1, which I already have here, so I'll ignore that. Plus or minus 4 divided by plus or minus 1 is the same thing as plus or minus 4. And finally, plus or minus 4 over plus or minus 2 is the same thing as plus or minus 2, but I already have it here, so I'll also ignore that. So my list of all the possible zeros, possible real zeros of f of x, this is it. This does not mean that all of them are, it just means that these are the possible ones. This is a list of all the possible ones. I can substitute each of them into this expression to determine which of them are actually zeros, but just by using the rational value theorem, it eliminates, because if I try to go trial and error, I could go on forever without knowing where to start or where to stop. Now in this example, we're going ahead a little bit more. We're using the rational zero theorem to find all the real zeros of f of x. Starting the same way, the rational zeros will be p out of q, where p is a factor of the last term and q is a factor of the leading coefficient or the first coefficient. So the factors of the last term, what you can see, the last term is -1, and the factors of -1 are simply plus or minus 1. The leading term, the leading coefficient is 4. The factors of 4 are plus or minus 1, plus or minus 2, plus or minus 4. So my combination of p out of q could be factors of the last term, which is plus or minus 1. Since there's only one, it could be plus or minus 1 over plus or minus 1. So this one over this one, or this one over this one, or that one over that one. So all plus or minus 1 over plus or minus 2, all plus or minus 1 over plus or minus 4. Now my list of possible zeros is this divided is plus or minus 1, this divided is plus or minus 1/2, and this divided is plus or minus 1/4. That's my list of possible values. So since these are the possible ones, this question wants me to find all the real zeros. What I'm going to do is start substituting each of these zeros into that polynomial, into f of x, to figure out which ones are real. So I'll start with f of, instead of plus or minus, I'll take 1 to start with, positive 1. If I put positive 1 in this equation, you guys can use your calculators to work this out. 4 times 1 is 4 minus 3 minus 1, I'll get 0. That means that that is a real zero. Alright, that's a good start. Let's keep going. If I put in negative 1, because I'm starting with this, I started with positive 1, then I'll put in negative 1. If I put that in here, this will be negative 4 plus 3 minus 1. Negative 4 plus 3 minus 1 is not equal to 0. Moving on, then I'll move on to half. I put f of positive half, that will be 4 out of 8. Again, you can use your calculator, you don't have to do the arithmetic in your head. Minus 3 out of 2 minus 1. 4 out of 8 is the same as a half, which is 0.5. Negative 3 out of 2 is the same as negative 1.5. So 0.5 minus 1.5 is minus 1. So basically this does not give me 0. Let me try f of negative half, the next one. This will be negative 4 out of 8 plus 3 out of 2 minus 1. It's a plus because negative times a negative. This is negative 0.5 plus 1.5, which is positive 1, minus 1, which is 0. So this is another one which gives me 0. So this is also a real zero of this polynomial. Keep checking. This substitution might seem like a long thing, but if you can use your calculator to type the equation in, and then you just set the x value each time, and then it will show you whether or not it equals 0. So you don't have to do the mental intensive calculations at this stage. Last one, if I put in a quarter, what do I get? So this will be 4 out of 64 minus 3 out of 4 minus 1. There is no way that is equal to 0. If I put in negative a quarter, how do I know? I'm pretty good at guessing. Negative 4 out of 64 plus 3 out of 4 minus 1, also no way it equals 0. So the only two real zeros that I have from this whole exercise are x is equal to 1, because 1 is the value of x that gave me a function value of 0, so x equals 1, and x equals negative half, because again negative half is the x value that gave me a function value of 0. So I have used the rational value theorem to find the real zeros of this equation. There's something else called the fundamental theorem of algebra. Now, you have encountered this before, just not, didn't have a specific name in the beginning. And it says that a polynomial of degree n has n complex zeros. Complex zeros meaning, when you look at these zeros, these are technically complex zeros. It's just that their imaginary parts are 0. So when it says complex zeros, the set of complex numbers is a set that includes both rational, real, and imaginary numbers. So don't let that scare you. So it says a polynomial of degree n, a function of degree n, has n complex zeros. If it has a degree of 4, then it cuts the axis 4 times, or it has 4 zeros, 4 complex zeros, including real and non-real zeros. And some of them may be repeated. We're going to look at an example. Maybe before we get to the example, so sometimes you solve an equation like x minus 2 power 4 and you only get 1 0, right? X equals 2. But since this function has a power of 4, you expect to have 4 complex zeros. Well, the reason is A, this is a repeated root, but the other reason is that some of those zeros are repeated, and when some of those zeros are complex zeros, and complex zeros come in conjugates. What that means is that if one complex number is a 0 to an equation, then its conjugate is also a 0. So suppose f of x is a polynomial function with real coefficients, then if a and b are real numbers where b is not equal to 0, a plus bi is a 0. So if a plus bi is a 0, then its conjugate a minus bi is also a 0. You're going to see how this works in an example. So just remember, imaginary zeros always come in pairs. Find all complex solutions, real and non-real, of this expression. Step 1, I can use the rational value theorem to figure out which ones are zeros. Remember rational zero theorem, P out of Q, P is factors of the last term, Q is factors of the first term. So it's going to be factors of 3, which factors of 3 are plus or minus 1, plus or minus 3, plus or minus 3, and this one is also plus or minus 1, plus or minus 3, plus or minus 3. So the options, remember each of these goes with each of these. The options are plus or minus 1 over plus or minus 1, plus or minus 1 over plus or minus 3, and plus or minus 3 over plus or minus 3. Second set of options is plus or minus, wait, what did I write here? The factors of 3 are just plus or minus 1 and plus or minus 3. Plus or minus 1 and plus or minus 3. Simple. Alright, so the second set of options is plus or minus 3 over plus or minus 1, plus or minus 3 over plus or minus 1. Simplifying this is plus or minus 1, this is plus or minus 1/3. I don't know what I was doing here. Plus or minus 1 divided by plus or minus 1 is plus or minus 1. Plus or minus 1 divided by plus or minus 3 is plus or minus 1/3. Okay. Plus or minus 3 divided by plus or minus 1 is plus or minus 3. Plus or minus 3 divided by plus or minus... what's happening here? Why am I confusing myself? Sorry, starting over. Rational zero theorem, P out of Q. The factors of 3 are plus or minus 1, plus or minus 3. This is plus or minus 1, plus or minus 3. The combinations could be this with these two, which is plus minus 1 out of plus minus 1 and plus minus 1 out of plus minus 3. Or the other combination is this one with these two, which is plus minus 3 out of plus minus 1 or plus minus 3 out of plus minus 3. Okay, so now what does that give? This is plus minus 1 plus minus 1/3 plus minus 3 over 1 is 3, and this is plus minus 1, which I already have. So since I know the list of possible zeros, I need to check which of them are actually zeros. I'm going to do that by substituting each of them in the expression of f of x. So if I try f of positive 1, I'm going to do this first. So if I put 1, all of them are positives, there is no way any of these positive numbers will give me a 0. So this is not 0. F of negative 1 is a possibility. So this is negative 3 plus 9, that is 6, plus 1, not a 0. Let me try positive 1/3, not a 0 for sure, because there's no negative sign here, so there's no way a positive number is going to give me a 0. You can plug it in and see for yourself. Negative a third is a possibility. Let me check. This will be 3 out of 27 plus 9 out of 9. So 3 out of 27 plus 1, not a 0. Positive 3, not going to be a 0 because again all of them are positives. Negative 3, this is the one which has to save us. So that would be negative 81 because 3 cubed is 27 times 3 is 81, plus negative 3 squared is 9 times 9, 81, so that's already 0, plus 3, sorry, negative 3 because I'm subbing for negative 3, plus 3, that gives us a 0. Yay! So 0. I know for sure that x equals negative 3 is a 0. That means x plus 3 is a factor. Now, since I know x plus 3 is a factor, I can find other factors using synthetic division. The coefficients are 3, 9, 1, and 3. And since x plus 3 is a factor, then my divisor is going to be negative 3. Step 1, drop the 3. 3 times negative 3 is negative 9. Add these two, gets 0. 0 times 3 is 0. Add these two, you get 1. 1 times 3 is 1 times negative 3 is negative 3. Add these two, get a 0. This is your remainder, and this remainder is 0. So my quotient is 3x squared. This has to be squared because this was power 3. 3x squared plus 0x plus 1. So my quotient is 3x squared plus 1. That means f of x is equal to divisor, which divisor was x plus 3, times quotient 3x squared plus 1 plus remainder, but remainder is 0. If I want to find the other zeros, I'm going to equate this function to 0. And already I know from this factor that x will be negative 3, which I already found here. It's only this one that I haven't yet checked. So 3x squared plus 1 is equal to 0. The 1 moves over to the other side. 3x squared is equal to negative 1. If I divide by 3, I have x squared equals negative 1 over 3. And if I take square root of x is plus or minus square root of negative 1 over 3. Remember, square root of negative 1 is I, so x is equal to plus or minus I square root 1 over 3. So my zeros of this function, all complex solutions, are, first of all, let me write them in blue. X is equal to negative 3, which is this one. X is equal to positive I square root 1 over 3, and x is equal to negative I square root 1 over 3. I hope you can see that this 0 and this 0 are opposites of each other, and this supports this complex conjugate zeros theorem, that if one complex number is a 0, then its conjugate is also a 0. So, and when you graph this equation, this is what it looks like. It crosses the axis only at one point, which is x equals negative 3, and has two turning points. So the zeros are this one and plus or minus that one. Descartes' rule of signs. Right. This is the last idea for today. So if I have a function or a polynomial with real coefficients, then the number of positive real zeros, positive, if I, when I solve for the function or where it cuts the x-axis, which are the zeros, the number of them that are positive is either equal to the number of sign changes. Sign changes is how many times the sign changes in the function. So the number of solutions, the number of intercepts which are positive for this function is equal to the number of sign changes, or f of x, or is less than the number of those sign changes by an even integer. I'll show you what this means in an example. And it still follows that the number of negative real zeros or the number of times it cuts the axis on the negative side, is either equal to the number of sign changes or of f of negative x, or is less than the number of sign changes by an even integer. Example. So the Descartes rule of signs to determine the possible number of positive and negative real zeros. If you look at f of x, we know that the number of positive real zeros will be equal to the sign changes or less than the number of sign changes by an even integer. English. So if I look at this and I'm looking for the positive real zeros, I'm looking for the number of sign changes in f of x. So the number of sign changes from negative sign to negative sign, that's not a change. Negative to positive, that's one change. Positive to negative, those are two changes. Negative to negative, that doesn't change. So the total number of sign changes is 2. That means that the number of positive real zeros can be 2 or 0. And remember, positive real zeros means the number of times it's cutting the x-axis on the positive side of the x-axis. And negative real zeros means the number of times it's cutting the x-axis on the negative side of the x-axis. So the positive real zeros are either equal to the number of sign changes, which for this function is 2, or they are less by that number by an even integer. How about the negative real zeros? Alright, negative real zeros, same thing. They have to be equal to the number of sign changes in f of negative x. So I need to first figure out what f of negative x is. That will be by substituting negative x everywhere I see x. Plus 6 into negative x squared minus 4 into negative x minus 12. If I simplify that, I hope you can see that I have negative x to the power 4, this doesn't change because it's an even power, plus 3x cubed plus 6x squared plus 4x, because it's double negatives, minus 12. How many sign changes do I have in f of negative x? I'm going from a negative to a positive, that's one sign change. Positive to positive, that's not a sign change. Positive to positive, not. And then positive to negative, that's a total of 2 sign changes. So the negative real zeros are also 2 or 0. Remember, I'm saying or 0 because the rule says that it's either equal to the number of sign changes or it's less than the number of sign changes by an even integer. So that's why it's 2 or 0, because you have 2 sign changes, but it can be less by an even integer, which 2 is the only integer that is equal or less than this. So it can be 0, 2 or 0, and then something 2 or 0. If I draw a table and try to list out, remember this question just asked me to find the possible number of positive and negative real zeros. It didn't ask me to find them, it just asked me to find the possible number of them. If I try to fill this out in a table, so the positive real zeros were 2, could have been 2, and if the positive real zeros were 2, the negative real zeros can also be 2. The complex zeros will be 0, and then the total zeros will be 4. The positive real zeros could be 0, and the negative real zeros will still be 2. The complex zeros, therefore, that means will have to be 2, because the total zeros have to remain 4, because this is a polynomial of degree 4, and being a polynomial of degree 4, remember, taking you back, that means that the fundamental theorem of algebra has to hold that a polynomial of degree n must have n complex zeros, right? Must have a total of n zeros, including real and non-real zeros. So that's why the total in this table has to be 4. The total of all the complex and real zeros has to be 4. Moving on, the positive real zeros could be 2, the negative real zeros could be 0, and the complex zeros could be 2, and the total is still going to be 4. Just showing you what this table is just showing us what the distribution of the zeros could look like for this function. And the last possibility is I could have 0 positive real zeros, I could have 2 negative real zeros, and I could have wait, am I getting, isn't this what this is already? I could have 2, no, I could have 2 positive and 2 negative, 0 positive, 2 positive, 0 positive. I'm messing this up, aren't I? Let's see. The positive real zeros could be 2, negative could be 2. Positive could be 2, negative could be 0. If this is 2 and that's 2, then the complex is 0 and the total is 4. If this is 2 and that's 0, the complex is 2, the total is 4. If this is 0 and that's 2, complex is 2. Oh yeah, if this is 0, this was the last option. If they're both 0, if there's no positive or negative real zeros, you could have 4 complex zeros and the total zeros remains 4. I hope that helps. This is